Hey everyone. Welcome to the Rust Bay Area Meetup. As usual, thanks Mozilla for hosting this space, and this time the food's from Commure, so you can thank them for the variety we've got this time. So today we have two talks. We first have Natalie from Solana talking about Berkeley packet filter in Rust, and then we have Ivan and Eugene from Commure talking about their experiences with Rust in production at Commure. Anyway, give it up for Natalie.
Hey, thanks, guys. It's Anatoly, by the way. No worries. It's Russian, so not English name. How do I get the display? Huh? Oh, perfect. So Berkeley packet filter in Rust. So our project is called Solana. It's a high performance blockchain. If you guys care about that, we can talk after. But this presentation is focused solely on the blood, sweat, and tears of getting a full Rust toolchain to compile to Berkeley packet filter. So what's Berkeley packet filter? It's limited bytecode created in '92. There was some guy working on a PhD for proof-carrying code and some folks thinking that they could build a self-updating OS, and somehow it ended up as a packet filter bytecode with 2 registers. And that ended up getting called classic Berkeley packet filter. But what it ended up doing, what actually ended up is a bytecode that's running inside the Linux kernel where untrusted user space can generate arbitrary programs, and those programs are sent into the kernel, ring 0, the most secure thing in your OS, and are verified and executed without memory protection. So it's kind of really, I think, a really fucking amazing achievement of engineering. So 2013, 2 registers doesn't seem like enough, and 64-bit register sets have been out for a while. So it was updated to eBPF, which is now simply called BPF, and this expanded the register set to 10 registers from 2, and added a bunch of 64-bit registers, and BPF backend was mainlined into LLVM. Same compiler used by Rust. So what's the architecture? Despite the name of being Berkeley packet filter, it's a full 64-bit virtual instructions. It supports 64 and 32-bit ALUs, add, sub, mul, div, but funny, no sign division. Sign integer division is complicated, I guess. But it's byte swaps, load and store, and jumps. So basically a full Turing machine. Has an instruction encoding that's fairly easy to understand. Looks just like x86. It's got a bunch of virtual registers. Program counter, R0 contains the return value, just like x86. R1 through R5 are the hold arguments for function calls, R6 through 9, call save registers. If you guys understand x86, this is basically one-to-one mapping from x86 to Berkeley packet filter. So why is this why this particular design choice? Because the Linux kernel, when it's doing its verification, really doesn't want to do this mapping of registers to whatever the current architecture is, because just about everything in the world and the most popular architecture is x86. So this pass of converting instructions to their native opcodes and to where the register placement goes in the hardware is very, very easy and very fast when you're doing the JIT verification. So what's interesting about Berkeley packet filter is doesn't have like a traditional stack where you're doing a push and pops of values. It just has a stack frame pointer, and the stack frame pointer doesn't move. So it's a base that's referenced for locations of memory in the current stack frame. So kind of think of it as passing arguments by the stack. You have all your data in the stack frame, and then you can reference the addresses based offset from the base stack frame address. Traditionally, BPF had this fixed size and number of frames and fixed call depth, but now they've added support for function-to-function BPF calls. So BPF in Linux must be verified before the kernel will accept it. It guarantees termination. The way it does it is it makes sure that all the loops, all the jumps, never actually jump backwards. So you can jump forward and you can jump backwards in such a way that it won't jump again. The kernel does this. Memory accesses are all safe, and all the execution paths are safe. And it can basically do this in a single pass. So the LVM compiler will spit out code that violates these rules, and then when you push it to the kernel will just reject it during the driver kind of initialization phase. So while the language is far more open, the way it's used in Linux is a subset of it. It's very used for effectively almost like a non-Turing machine event handler. So it's a single object file. There's no relocations, no data sections, and has very limited built-in helper function supported. So if you guys look at the object dump, it kind of looks like that. Still very similar to x86. So there's some use of LVM outside of the kernel. And this is, I think, the blood, sweat, and tears of work. So we took LVM with a modified BPF backend and built in like multi-file linking, so you can actually link in a full ELF. You can have an ELF specified entry point, so you generate this ELF and then you tell, hey, look, jump to this address at the start. You have load time relocations. We added load time symbol resolution, read-only data segments, some PC relative jumps. And now you can pass and return aggregate types on the stack frame, which if you're returning a vec, that's an aggregate type because it's effectively a structure of pointer and length, and I think that maybe something else. So you can still only modify data passed into it, so there's no writable segments. So imagine a program without any writable globals. I don't know if this stuff is like way too deep, but so outside of the Linux kernel, runs in a virtual machine, which guards memory accesses and maximum instruction counts and function call access. So we also have a preliminary JIT to x86 support. And what our real goal is with this is to take BPF and convert it and JIT it to GPU code, because GPUs have 4,000 SIMD lanes, 60 thread contexts, all this silicon that you can use for these very small programs that have very little stack. Why BPF and not WASM? So WASM is kind of like this big cool thing, new bytecode, new stack-based VM. BPF has been used in production on a single machine, single socket, to process 60 million packets per second, so 60 million events per second on a 40 gigabit network. It's a big pile of data, a massive amount of events. So it has this like really nice proven architecture for speed, but it's also safe. Like this stuff runs in ring 0. You take this code, it's compiled down to bytecode, and then you can send it to the most secure, trusted space in your hardware. And because of the simplicity of the register set and how it's designed, it's maybe the most opposite way you can go from a stack-based VM, because there's no like actual stack register, there's no push and pops. It's very, very simple to verify. And that's, I think, a really compelling use for it. And the reason why it does this is because of all these limitations, right? It's got limited threads, this very simple stack frame, and all this stuff that basically makes it impossible to write large-scale programs like you would want to with WASM. So why Rust? Finally, getting to adding support Rust to BPF. So our project itself is written in Rust. Rust is friendly, Rust and safe and fast. If you guys are working on Rust, I want to thank you for making a language that I'm like happy to code in. It's just wonderful. I spent 12 years working in C, and like it's just awesome. couldn't be happier. So Rust natively uses LVM for its backends, so should be easy, right? Just like take this backend, switch this thing, and that. No. So basically everything you can think of blows up. Rust often requires things like memory allocation, system dependencies, create dependencies, pull in like every kind of thing you can imagine. And the environment that we need is single-threaded, no networking, no standard IO, no general purpose allocation, so no mallocs, limited support for panic. So if you take Rust code, no standard lib, so no STD crates allowed, single-threaded, with all these restrictions, you can compile it to BPF. After you do all these other things. So BPF is not a built-in target, so custom Rust is required. So we added a new target in our fork. We added a new ABI modifier to BPF. All Rust sysroot and SIMD and all these built-in libs require modifications to accommodate. We can't do 128 bits. We can't do some floating points because there's no support for signed division. Signed numbers are hard. But this awesome project, Xargo, I don't know if you're working on this. It's a wonderful project. You can kind of take all the stuff that we forked and put it together into the package manager. It's great. So all this work is actually very easy to leverage. There's a big pile of stuff that still needs to be done. So for us specifically, reroute all the standard outs, standard error to specific logging functions. We want to provide a limited and isolated memory allocator. So when the VM is initialized, we can kind of say, here's some memory for the heap. So when you run this bytecode and it calls malloc, go jump to this particular page and get memory out of there. And hopefully at the end of the program, all the memory is cleared. If not, sorry. Debugger support would be nice. The output is ALF, so dwarf files, you can generate them, so you can connect to debugger. Support for 128-bit types would be great, simply just to keep parity with Rust itself. There's like tons of unexpected gremlins. So panic info is like not reported correctly at all. LLVM is a beast. It'll generate code without errors, but when you look at the code, it's just like random instructions in there, and it's impossible to really trace where the hell they came from. If you guys are LVM experts, love to talk to you. You can go to a repo and try it out. It's a work in progress, but it's actually fairly useful now. So for a particular project, these programs are single-threaded, really don't do any I/O. They're just event handlers, getting some data, processing them, and modifying some memory. And that's the only output, is that modified written memory. There's an issue that's kind of tracking all the things that we're working on. And you can go fairly easily try this out. So there's a bunch of references on BPF. It's a really cool project. This company, Cilium, is doing a lot of work in this space, and they're mostly using it for software-defined networks, but they've really added a ton of tooling and support for BPF, and especially in the Linux kernel. You can find our customized BPF VM on our GitHub and some example programs. And if you guys want to roll up your sleeves and fix these bugs, there's a forum. If you give me your email, I'll email you guys, and maybe we can set up a meetup, have some beers and pizza, and fix a bunch of these issues. That's it. Any questions? Yes. Yeah.
Cube is no more.
Yeah.
We have these.
Oh, this one works.
Yep.
Sweet.
We can't throw these.
So I assume that you're using eBPF due to some sort of termination smart contract guarantees or something like that. Does that mean you're willing to modify eBPF spec to support things like floats?
Yeah, so the reason for BPF isn't that the guarantees, because you can use an instruction counter with a similar property. So the Linux kernel does this check where it just looks at all the jumps, make sure that they don't create loops. Instead, you can like add the number of instructions the jumps are jumping until you run out. So you can basically get around those problems with very dumb tools. We're using BPF because our goal, like in our particular project, we're constrained by the resources of a single system. It's a fully replicated state machine. There's no way to split the state. So that means that we want to really maximize the available compute. And the only way to do that is with GPUs. Unfortunately, there isn't like a stable GPU bytecode that we can go to. And BPF is so dead simple that you can look at this bytecode and map it directly to CUDA or whatever else is going to come next. Does that make sense?
So you're just using eBPF as an IR.
Yeah, exactly.
But that does mean you're willing to modify the
Yeah.
IR. Okay, cool.
But what's great about eBPF is that nobody in the Linux kernel is going to add something that'll like we won't take, right? They're not going to upstream a change that'll break security or performance because they're running this thing in the kernel, right? So they're really like fairly good constraint, and what we're doing is a superset of what they're doing. But we'll never really have to worry about like, being a total fork.
Cool, thank you.
Go ahead. Yeah.
Hi. Does the bytecode run on the kernel, the one that you generate with your Rust tool?
You can run it in the kernel, yeah. So the tools that we've done so far, nothing. We haven't broken compatibility with what the kernel verifier will look. It's still LVM output BPF.
Yeah. So you could replace BCC with this Rust toolchain?
You could. BCC is still, I think, a better choice, but like because of how much Rust pulls in out of like malloc and stuff like that, it'll be pretty tough. But it's getting closer. That would be an awesome like outcome. Is that there's a full featured like Rust way to do BCC, right?
Yeah. I would be interested in playing with it. Thank you.
Sure.
So you mentioned that LLVM is a beast. The other project that sometimes contends with LLVM being a beast is Rust-C, right? So there's been talk of trying to add a CraneLift backend to Rust. Have you looked at CraneLift at all for use for the purposes of BPF?
No, I haven't. I'm not familiar with it. Cool. CraneLift. BPF is like a very, very it's like a toy backend. Like I think if you have an intermediate language that's generating to machine code, BPF would be maybe the easiest thing to add. It's called CraneLift?
CraneLift.
CraneLift, cool. Is that any more questions? Cool. Thank you guys for having me. The food was really good. I just emulated maybe. It's like...
All right. Hello.
All right, I need to.
Okay, so next we have Ivan from Commure talking about Rust at Commure.
Okay, stop working. working for me again?
Yeah, this is the mic to hand out, but I can come fetch it later.
Oh no.
Yeah, that's-
All right. So, hello everyone, my name is Ivan and I work for Commure, and today I would like to tell a couple of stories about how we use Rust at Commure and what kind of like challenges that we had while working on their application that we're building. So first, I would like to start with who are we? So we Commure, we are like a stealth startup, and we are working on fixing the software doctors use, and that's our kind of like a sales pitch for hiring. But what that means, and I'll tell a little bit more details later, like what exactly that means for our like Rust part of what we're building. And I also want to include this. We are hiring, so if you're interested in Rust and you want to work on Rust 100% of your time, you can apply at this email address. And a couple of words about our backend. So we're building like different things, and some of the like front end pieces, on the back end pieces. I'm going to be talking about like back end pieces specifically. A couple of notes about backend. It's written completely in Rust with bits of C code, because unfortunately not every library was written in Rust yet, unfortunately. So we have to use C, but they're like really small libraries. And it was pure Rust from the day one. So we never had like Python code and we were like pushed into Rust because of performance issues or something like that. We started from day one, like building the whole backend, the whole application in Rust. And at this moment, it's 100,000 lines of code, more than 50 crates. So it's kind of like an enterprise software we're building. It's not like one particular library. It's like the whole stack. And I would like to give some of the details, like some ideas, like what that enterprise software means. For us, the enterprise the enterprise software, that's a kind of vague term that can mean everything. But for me, it means things like APIs and data transformation, interoperability, data security, kind of like this kind of thing. And one big challenge of building enterprise software is to have complexity like everywhere. And if you read some like discussions on like Twitter or internet, that people like looking for simplicity and like they're asking questions, are you really solving the problem and making it simpler, or just like shifting the complexity around? So for enterprise software, the answer is pretty much like you always just shift the complexity around. Like it's like you cannot make it simple. It's like very complicated. And there are like a number of reasons why is that happening. And one of the reasons is that it's just like the data models, they're trying to model the real world, and real world is complicated, and you cannot really change that, so you have to just like follow that, and your data models become super complicated. Then you have things like regulations. They're completely outside of your control, like mostly outside of your control. Is that they like keep coming up with some like new regulations on law, telling, well, maybe starting from tomorrow, your data have to be available in this particular API. And then like a week later, we're like, well, we actually found that was not a good regulation. We're going to change that, and like there's like a different standard you have to implement now, and you have to comply for that. And there's also things like legacy software is like a lot of pieces were built before you built your own application, and they already exist, and you have to like deal with that somehow. And that would be like old legacy data standards, legacy APIs. In some cases, wouldn't be even any API. There's like some software working somewhere. It kind of works. Everybody's happy, but nobody knows how to even like talk to that software because like all the documentation was lost or something. And there's a lot of requirements on the security side. And I think the kind of like the theme of enterprise software is like it's all about like the scale. It's complex in all dimensions. It's complex like in time, so like the projects takes like years and years to build. There's like the software like we have to deal with standards built like 30 years ago. It's also scale in terms of like people, organizations involved. Like if you take the whole healthcare as like an industry, there's like regulations, there's like hospitals, there's like insurance companies. There's like a lot of complexity coming from that. And what I kind of found is that the main theme of working this kind of software is to being able to like separate, kind of like compartmentalize everything. So build your software in like pieces and make those, it's a kind of decouple everything into smaller manageable pieces, which is kind of like obvious, but I think in enterprise software, it's kind of like really like, I was having discussions related to Rust and like Hackers News, and what was one of the themes is like, well, why won't you just like go and switch this data structure to that data structure? And it's like, well, if you have like 1,000, 100,000 lines of code, you can't really do that. You start changing in one place, and and then like it'll take you like days and days and days, and then at some point you'll find, oh, well, actually that new data structure doesn't satisfy that particular requirement, so you cannot really replace everything. So it's important to build those boundaries and make everything work kind of like across these boundaries. And one of the important principles becomes you need to have really like a loose coupling. And I think this is where Rust presented us with some of the challenges, and I'm going to highlight them in examples I'm giving. Another principle is, and maybe that's because we are like early startup and we haven't really learned everything about the domain they're working for. We're still building an expertise, so we don't know which answer is correct. So like it's very important to like avoid one-way doors. And I would think that this is sort of like an extension of this loose coupling, but for design or architecture you're building. So whatever you design, whatever like component you designed, you cannot just say, well, that's the way to build it, and like switching to that way of doing things, like starting tomorrow, because that would be this kind of like one-way door decision. So what you have to do is to build it on a side, make it kind of work, observe how the whole architecture develops, and then maybe finally you're making a decision like, yeah, that thing actually works better, so we're gonna switch to that, doing it this way. And just in general, like you have to accept trade-offs. There's like no perfect way of doing things, like no simple ways. Like you can chase the simplicity for like months, and then you'll find more and more nuances. So it becomes important just like say at some point, well, that solution is good enough. Like let's move on to some other part of the system and work on that. And since everything is like loosely coupled, hopefully, then you can kind of still make it work. Like the old parts of the system, the new part of the system. And one of their and I like to call it, it's like a waterbed architecture. It's like you have like a waterbed, like a bed filled with water, and you want to like compress it. The thing is, like, it's easy to compress it on one side, but it'll like pop on the other side. So that's kind of the architecture. Like you're not really solving you're not really making it simpler. What you're doing is you're shifting the complexity in a way that it gets off the ways that are important, and it moves to in the places where it's like less important. So hopefully you're moving complexity from part which is, let's say, facing to application developers, and you're moving that complexity to the area where like more like system developers build, like the framework builders kind of work in. And I would like to give a couple of examples where we had some of the challenges that Rust presented us while building the software that we're building. And first example would be like lifetimes. So lifetimes are great in Rust. Like they really help you to keep your data safe, and they save you from like data races. And if you can, sometimes you can even map more high-level requirements, like, well, while I'm using this particular object, like that other object should not be accessible. So you can express that in terms of lifetimes, and it can help you to maintain that invariant. But one unfortunate property of lifetimes is that like they proliferate. They tend to proliferate. Once you put a lifetime on your struct, like it's over. Like you cannot get rid of that lifetime. Like if you put that struct in some other struct, it has to have the lifetime too. And if you like do some impulse for that struct, it also has a lifetime. So like the whole system becomes infected with lifetimes at some point, which is not great. And that sort of creates two worlds in Rust. Tends to create two worlds. In one world, you like own everything. You have arcs, you have RCs, you have ref cells, and the other world, you're just borrowing everything. And sometimes it's very difficult. It's very hard to switch between those worlds. So the example would be like you have destructive lifetime. Now you need to put it into arc and maybe send to other part of the system that is like completely like remote from the part that you're working on, but you cannot do that because it has its lifetime. And there was one particular example which took a while to figure out and work it through. And there was this connection in Postgres crate, and there was this transaction in the same crate. So the connection was the struct without lifetime. So you can put it in whatever you want. You can put it in an Arc. You can send it somewhere. You can put it in RefCell. Like do whatever you want. But there was also the transaction thing which modeled the SQL transactions in a pretty natural way how you do that in Rust. The transaction would borrow from connection. And actually in the new version, I think they changed this shared borrowing into a mutable one, which expresses invariant even better, is that now you can only have one transaction active for that particular connection, and unless you drop your transaction, you won't be able to do anything on a connection because the connection will be borrowed by this transaction thing. But unfortunately, that creates pretty strong limitation, is that now you cannot, like if you need to pass the transaction around, you have to pass it with those lifetimes. And that's very problematic. That was problematic in our case. And why is that? Like, why not just have lifetimes? You can just put the lifetimes on these whatever functions, and most of the time, compiler would even like allow you not to specify them because there will be runtime illusion. But in our case, it was complicated. Again, there was like many different pieces, and one part of the system was specifically requiring us give us some reference to a T where T was some sort of context, and the T has to have a static lifetime. And that part of the system was related, like completely unrelated to a part that was creating transactions. So there's one part creating transactions, and there was another part implementing the GraphQL API, which required that you needed that transaction to implement the GraphQL API, but it also required the type parameter T to be static. And that wasn't like, that was, and it was like this observation is that, well, if you look at the connection and transaction together, they don't really have outgoing references. So it should be possible to somehow duct tape them together and just say, well, now they don't have lifetimes anymore. Like now you should be able to put it in Arc or like put it in whatever RefCell or like move it around. But you can't do that because that would be a self-referential data structure, and Rust kind of like doesn't support them, doesn't like them. I haven't seen opinions saying that, well, if you like need self-referential data structures, maybe I'm not using Rust right. Where like I think that was like a real world example, is that we're taking this library, we're taking this warp component we have in one part of the system, we're taking this another library, we're trying to combine them together, and they just don't match. And like at this point, it's not like about finding like the perfect way of doing that. It's just like give me some sort of duct tape so I can just like make these pieces to work and buy some time, and maybe later we'll rebuild this part of the systems just to make them work better with each other. Like I need some sort of solution like right now. And we found that solution. It was a rental crate. So somebody created a crate that allows you to create self-referential data structures. I think that a lot of like this small fine text warnings is like, well, I think I've seen a post by the author of the crate saying something like, I'm not sure that this crate is like completely sound, like might introduce some unsoundness. But at this point, it's like I'm desperate, like I need some sort of solution. Like it's better to have this kind of guarantees versus just, well, I can't ship anything because I can't build anything. It's like self-referential thing, and I'm done. So so it kind of provided a solution, and it allowed us to create this struct. That's the way you express this struct. You say, hey, I have this field connection, and I have this another field called transaction, and it uses this lifetime, which is named after the field. And by some magic, this rental crate would transform this struct. I think it transforms it into some weird thing. It probably uses boxes or something to make sure that the address of the connection doesn't change. But it allows you to kind of like do exactly that, what I mentioned before, is just duct tape those things together and just forget about this problem for a while. And this kind of solved the problem at the point. So so the outcome is that sometimes you need some solution that probably nobody should ever use, but if you're really like in a pinch, you have to have something. It's better to have that solution versus just saying, well, like we can't move forward. But later we actually rewrote the code not to use that transaction. We create our own wraparound connection, because you can have a struct that owns connection fully and also manages transaction, and then you wouldn't have this problem in the first place. But what rental allowed us to have is to just buy some time. It's just like do it in a like whatever, not being pressed by the time limits. So that was one of the examples that we had. There was another example which took me a while to figure out fully, and maybe that's related to like me not really having a lot of Rust experience at the time. That was error handling, and there was like a bunch of requirements which I came with originally, which I wanted this error handling in our system to have. And one of the first requirement was it should be possible to just chain multiple errors together. It's like natural requirement. If you have lower level error, sometimes you want to add some more context and wrap it into high level error, and maybe you do that multiple times. So an example could be like validation failed for a particular object. That'd be like low level error. And then a high level would be, well, that happened while we were validating that particular instance of data, like with that particular ID. And then on a high level, it would be, well, this whole thing happened while we try to process that message we received from that system. So it's kind of like natural requirement to being able to add more and more details. So another requirement was, because our parts of our system are supposed to be like loosely coupled, and we use dynamic dispatch a lot to achieve that, in that particular setting, sometimes you don't really know what's the error type you will be receiving. Because if it's a trait object and say it implements like a data loader thing, it could be implemented as a data loader from file system, from database, or from in-memory. They would have like completely different sets of errors. Like the database one would be some database-specific errors. So we needed some sort of like an error type which can package any possible error. Something similar to box of std error. Like you can use box std error for that. And then there was another requirement. It would be nice to have backtraces so you know where the error happened. Like in an ideal world, you should never need backtraces. Like your errors should be like very well structured, and they should contain like all the information that you need. So whenever error happens, you look at the error and it says, well, this happens at that point, this happens at that point. But in real world, a lot of errors are just like, well, something happened and we have this error type. It doesn't have any data in it, and you have no idea where it's coming from. So if you have a backtrace, at least you can look at that piece of code and maybe make a couple of guesses like why did that happen. It's more like a pragmatic choice versus like a perfect thing. And also, we're trying to avoid using panics and unwraps as much as possible, because if you have a long-running server, there's some consequences with panics. Like your panics might cause your mutexes to be poisoned, and then at that point, your server is basically done. You can't do anything because the mutex you're sharing across the whole system is now poisoned, and now you cannot lock it anymore. So instead of using panics, what we're using is we're using those concepts of like internal errors. So if you're getting in a state where we shouldn't be ever getting, but we still got in a state somehow, we return it as an internal error, and internal errors contain backtraces, so you can track it back and try to understand like why that particular situation happened. And then there was some other like more application-specific requirements. Is that it would be nice not to require application developers or whoever is developing different components to use any specific error types. They should be free to design error types the way they want them, and not like just use some weird specific error types that we provided. Because again, like it's a big system, you can't really enforce that on everybody. It's just you have to use that way of doing errors. So it should be like loosely coupled. But it also should help with boilerplate, because if you need to derive some like display trait for an error, like it would be nice to have a mechanism to just derive that versus implementing all this trait by yourself. And those 5 requirements was like they're not too complex to implement, like all of them. But there was also another requirement which kind of like changed the whole thing and make it like way more complex, at least for me. We also needed a way of getting a structured information outside of errors. And the reason for that was the standard we were implementing on our APIs. It required that whenever you call an API and you're getting error, we are not supposed to just return like a text message. We're supposed to return like a structured JSON saying, well, that thing happened, error of that code, that diagnostic message, and then some detailed information for errors, and not just like the error message. And that particular requirement was hard, and I'll explain a little bit later why. So for the first flight, you just like take failure crate, and it just does that. It was great. Like I pretty much randomly chose that crate because I knew nothing about Rust at the time, and I was like looking how do you do errors, and I found out this failure thing. And it turned out it was like a great crate. It's just implemented all the first 5 requirements for us. Like we didn't have to do anything. The remaining one was difficult, and the reason for that was being able to get the structured information out of errors meant that all errors supposed to implement some sort of trait. So let's say we have some trait called extra info, and all errors which could provide some structured information supposed to implement it and have this function info that will just return an option of some info, and info would contain all the structured information about this particular error type, this particular error instance. But the problem with that was that you have this chain of errors, and failure crate allows you to go through that chain and scan all these errors and like look at them. But how do you get this trade object of X trained for if you only have the trade object of fail? So the trade object of fail is what the failure crate would give you if you iterate through errors in a chain. So that was like a problem of cross-casting trade object to a trade object, which is not really a thing in Rust. Like in language like Java would be not an issue, just like cast and everything works fine. For Rust, there are no solution. At least like I wasn't able to find any good solution. But the idea was that, well, we can use downcast ref. There's a way of downcasting from fail trade object into a specific error type. So we can use that. But the downcasting only works for concrete types. So how do we know which concrete types you have? Because remember, like, everybody is free to declare error types, like as many error types as they want. So we don't really know. So our error subsystem doesn't really know. That doesn't really have the whole list of all the error types we're using. So that was problematic. And one idea was like, well, we can have some sort of registry, like a hash map, mapping a type ID into like a cross-casting function. And a type ID is something that the Rust compiler can provide you. It's unique identifier attached, like every type in a Rust type system the Rust compiler could generate this unique identifier for every type in a Rust system. So if you know type ID, you kind of know what's the real type behind this trade object. So if you build this map, and then you register all the error types in this registry, and registration would be, you just basically go and for each specific error type, you can put a mapping from the type ID of that error type into a function that would be just downcasting to that specific type and then immediately generating a trade object of extra info. But now the problem is that, well, still, how do we enumerate all the errors? Like, we haven't really solved that. So this is a kind of approach, but the problem is that how do we enumerate all the errors? And I was looking for a long time for a solution. There was like different ideas, like maybe we can build a compiler plugin, so whenever we declare error type, you like annotate it, and somehow this compiler plugin would generate a code that would like register all the error types. We can build like a tool that will scan our source code and find all the errors. Or we can like manually register all error types. That's the approach we took originally. We were just like explicitly registering all error types in the beginning of our main function. But it would be nice to have a way of running some code before your main automatically, like a static initializer. But they tell you like, well, there's no static initializer in Rust. You shouldn't even have them. It's a terrible idea. And like, I agree, it's a terrible idea. But this is, again, an example where, well, like maybe I know what I'm doing. I promise I'm not going to do like sophisticated stuff on the static initializer. Maybe I'll just like build whatever, a simple list of pointers, references between those error types, like something really that I guarantee that's going to be saved. Like, I'm not going to tell like other developers how to do that, but like I want that for myself just to make this error handling working. And I found the solution. So I was before doing this software for Commuter, I was doing the hobby project for embedded, and I remembered, well, in the embedded world, you have like a lot of power by just using some linker magic. You can like put something in linker section. So I had an idea. Maybe you can, for each error type, you can generate some function, and maybe we can put an address of that function in a special linker section, and then at the beginning of the main, we would just scan that section and just call this function, and those functions would register the error types. But turned out that somebody had already built a crate called CTOR crate, and you just put annotation on a function, and it runs a static initializer. Like, you can have that in Rust, but you still have it. And I think it's very important for, especially the kind of software we're building, to have those like escape hatches, because we can't take no as an answer. Like we need to ship something. We need to like build a solution. Might not be perfect, and there's a discussion happening. Is like if this whole crate should be marked as unsafe? Does it introduce unsoundness? It might introduce unsoundness because a lot of operations you cannot do before your main. For example, the crate itself gives an example. You shouldn't do any output to STD IO because the output subsystem in Rust is not initialized yet. I'm not sure like if you can use like a memory allocator at that point. Like maybe you could. It seems like it works, but maybe you shouldn't use it. Maybe some memory allocators would not work if you use it this way. But again, like that's a solution that kind of allows us to continue working on. And then once we have this, that becomes very simple. So we can hide it behind a nice abstraction. So we can have this derive extra input trait, which behind the scenes will use that annotation. So like, I'm not going to tell like anybody how this works, but it's like magically it works, and it seems like working well so far. So like problem solved. That was like another kind of like duct tape, which we like used to just like make things work. And those are third examples. Third example, and unfortunately, that example is not like it's not solved yet, but I'm just going to give it as an example of another kind of problems. What we had to solve with Rust, which were particularly challenging, it was just modeling the healthcare data. Overall, the problem looked like there are some data schemas given us by third party, and they're simple in the sense that they're not using any crazy like type things. They're like just structs and fields, and those structs, that fields have types, and types could be like lists of other types. They're like pretty simple, but they're numerous. There's like hundreds and hundreds of them. And then, yeah, so there was like about 200 top-level types, 1,000 structs in total, 500 enums. And that presented like a little bit of challenge because like if you just generate that amount of structs and you start building like functionality for them, maybe like short-day deserializers or things like that, that slows down compilation by like a lot. Like our compilation times, like it's probably one of the like top 3 issues that we're having right now. And whenever we so that's kind of like the set of challenges here. And there's also like several versions of them. At some point we said, well, you know what, actually we have to multiply that by 3 because now we have 3 versions of the standard we need to implement. And the standard provides formal schemas. So the idea was that we can use those schemas to generate the code for us, so we don't have to like manually type everything. And there are like many nuances. It's like I'm still like keep learning about like these tiny little things about the standard. They would do like terrible things. They would publish a schema and say this resource is stable now. We are not going to change that, but that particular field we can change. Like we can still change it in future revisions. It's like how is it stable if it's like have like unstable? Like what does unstable then means? But there's like very nuanced. Like, well, but those fields, the other fields, they're not going to change. Or they like, would give you a list of items and specify that and say, well, the list is stable, but the contents of that list, and the list could be like enum, is not stable. It's like, how is that stable? And they're like, well, the nuance is that you can rely that definition would exist, and each definition is annotated URL, like there's a whole set of metadata available. You can rely that would exist, but what they would put in the list, that might change in the future version. So there's a lot of these like tiny things which we're still learning, and they make this problem like really hard because at some point, like for example, we wanted, well, maybe we can extract some commonalities between those versions, or like generate like for stable types, generate type 1s for all the versions in each stable. But then it turned out that even that is like very difficult for these reasons. It's like, yeah, it is stable, but it still might be different. Like a newer version, they still can change that definition. And for this data we were modeling, we needed pretty basic operations so far. Is we need to deserialize and serialize them. Obviously, like we need to read JSONs or XML and write them back. We need to validate them in a type agnostic manner, in a sense that sometimes, so we need to be able to validate them according to the built-in definitions provided by the standard, but also the standard allows you to define your own set of constraints for those data types, and we need to be able to validate data against that. So for example, hospital can create their own set of constraints and say, well, in this hospital, the patient have those additional requirements and these additional constraints, put it in a formal definition, and then give us, and we should be able to validate patient against that definition and say if it's valid or not. And then this standard is like really crazy. They pretty much redefined the whole world for themselves, and they defined a language which you can use to extract data from your data types. So similar to XPath or JSON path, they created a language with like its own syntax and semantics and how you like all of these things. And we needed to build an interpreter for that language to be able to go into data we received and run particular expression against it and return data evaluated by that expression. And the simpler requirements is that sometimes in a code we just need to create a new instances of this data. And we also need to consume instances of this data in a type-safe manner, so that if you're building a piece of code that works for a specific data type, it should be possible to read the JSON, get the Rust data types, and just work directly against them. And we had multiple options how that could be handled. How can you model this data? And initially, well, one option is obvious. You just take all these data schemas, generate Rust code, everything is fine. There are some nuances. It turned out that whatever data schemas they give us, it doesn't really match what they have in JSON. Like they would define like a semantical model, but then it would be like a separate part of specification. By the way, in this particular case, that field doesn't map like one-to-one to what you see in JSON. And that made it like crazy. It's like now you have an option. Either you model your data based on semantical model, and then you cannot use like, let's say, sorted to serialize it because the JSON doesn't match struct. Or you can generate struct based on JSON, and then the whole application code you're building need to remember that whatever you see in a struct is not really what the standard defines. And then the other option would be, maybe you just don't care about types, just load it in the sorted JSON value thing, because use like dynamic types, load JSON in it, and only apply types where you need them. So for example, if you're doing validation, you would retype information dynamically. You would get the sorted JSON value and just kind of like go through both of them simultaneously and verify that everything matches. And there are some other more exotic options, is like this favorite Rust like vector plus indices data structure, which allows to kind of like bend some of their Rust rules. And the reason we needed that data structure is that this standard also defined another language which we needed to implement, and that language would require us to have shared mutable references to the data. And this is something that like is completely against like a Rust borrow checker. A borrow checker would never allow you to have that, and this language is like, yeah, fine, it's possible to have two variables pointing to kind of like the same thing, and both are like mutable. And like I have my theory like why that happened. I think like they defined a standard looking at like languages like Java, which like don't care, you have like multiple references, you can modify whatever you want, but they didn't really think about all this like potential semantics, is like what are they like about like data races and things like that. So to kind of support that language, we had to implement another data structure. And then at some point we had all four of these ways of doing the data, of modeling the data. And that again goes back to this loose coupling and being able to not having this one-way door. It's like we would model in one way, and other part of the system we need to model another way. So we needed to develop a way for like our parts of the system to work with all four of these representations. And we came up with some sort of like a common API which would be implemented for all these data structures. So we needed a way to work with this data in a generic manner. And this API was some sort of like a generic reference type, which is like a trait, which allows you to basically remove, like go from static typing to this like kind of like the world of dynamic typing. Like in JavaScript, you go into object and just index the object by string. So we kind of implemented that API. It allows us to like get the value, like given some reference to the data, you can get some like primitive value, for example, number or string or something like that. And also allows you to go inside a field, and if you have a field name, you can go and check what's the reference to that field, and get some type information for the data type too. Unfortunately, that API worked only to some level, and then we got to the point where, well, we need the mutable references. We need to be able to mutate data using this API, and it turned out that to express that in traits, you need GATs, which are generic associated types. And it mostly goes to that if you want to mutate data, you want a function called like getFieldMute, and it should take self as mute self, and it should return something that borrows from that self. But that something is what the type of that something will be defined by the implementers of this trait. So it will be like associated type on this trait. So you need an associated type which is parameterized by lifetime, and that lifetime needs to come from this mute self. But long story short, it requires a feature that is not available in Rust, unfortunately. So the other consideration was, well, if you go this static type way and you use these traits, the compilation times becomes terrible, because all your code that is parameterized by the type T implementing this reference will be monomorphized in a multiple version for each data structure. Basically, if you have a validation code using that reference, you will have like 4 versions of this validation code emitted by compiler. Because for every possible implementer of this reference type, there will be like a copy generated, sort of. And that increases binary size and increases completion time. So the solution that I kind of like reached to is like, well, maybe you should go with trait objects. It's not something like, in a Rust world, it's kind of like this tendency, well, the trait objects, not like you're supposed to use static polymorphism, and there's like the power of Rust and everything. But I think for enterprise software, it's more important to be like decoupled, and I don't know. I think the trait objects are fine, because we're not working on like kernel drivers, which has to like have this perfect performance and everything. And trade objects, as a side effect, they work very nicely with borrow. So you can even have this mutable access. So if you have this get field mute, takes self by mute, it can return reference to this another object thing. And the borrow checker will make sure that while you're having this borrow on these children, you cannot modify the parent. So like everything works in a very natural way. But unfortunately, like the trade objects, harder to make them work for other types. They work nicely for structs. So if you generate struct, you can just directly implement the trade objects. And the implementation would be like pretty straightforward. So whenever somebody asks for a field, you just return reference to the field. But there are some challenges. Like you can't really make them work for, let's say, for vector. I mean, this is data structure. Because there's nothing to borrow from. You're not borrowing something that already exists. You need to create something. I have some ideas how that could be. Like if you really, really have to, like, again, like this one-way door kind of thinking. I explored other options, like how can we make this trade object work for other data structures? Seems like it's possible, but would require some like sketchy things to do. And I think, I don't know, just kind of the conclusion is like, I found the trained object are really awesome in Rust. I think they're really, really powerful. And I wish if there was like a little bit more work and like standardization happening around trade objects. Like I would love them to have like a stable ABI or even more like crazy things like being able to create our own trade objects by creating your own like vtables at runtime, like things like that. I'm not sure if Rust will ever get that, but would really help to build like these lower level things. And one thing I was concerned about trade objects is like everybody says, well, the performance would like suffer. First of all, like you're doing this dynamic dispatch, it is slower, but more importantly, you're not letting compiler to look through these trade objects and do optimizations, which would be available otherwise. And in the end, so what we ended up with is we have regular Rust structs. They implement those set of traits. They use macros to derive those trade objects. We have custom JSON XML serialization that uses those trade objects to deserialize data. And what I was curious about is like, how do we compare to Serde? So we had these original structs which used Serde for deserialization, and now we build our own deserializer which uses those trade objects and those dynamic dispatch to load the data. And like performance-wise, and it turned out that it was like two and a half times faster for some reason. Like I'm not quite sure why. I think there's numbers like. I think there's something I'm missing there. It's not exactly apples to apples comparison, but loading the same data types into like the old structs just using Serde, or using them in a new data types using our dynamic dispatch. It is like dynamic dispatch based serializer is like 2 times faster at least. And the binary size dropped because Serde generates like a lot of codes. For those thousands of structs, it generates like thousands and thousands of those functions to deserialize those structs. But in case, when you're using trade objects, we have like one copy of deserializer. It doesn't care. It just gets a trade object as a parameter. And compilation times seems to be faster, which is also good. And that was like the third example that I have. And final thought, I would say building this kind of software in Rust was really, really fun because I had to figure out a lot of things that I'm not sure like, I think we are kind of like using Rust in a direction where, not in a direction that was like, I would consider like as a primary direction of Rust. So we're using it for enterprise software for like building applications. And I think only recently people started using it in this. Originally Rust was more like a systems language for replacing C and C++ or doing like high performance things. So I think it was fun to figure out a lot of these things ourselves. I would say that I found that parts of ecosystem language are like a bit immature, which is expected given the Rust age. And there are some interesting engineering challenges. And that's all I have. So, and as a last item, I'd like to, we are using Rust a lot, we rely on Rust a lot. We should be contributing back to the community. We are not really contributing a lot at this point, but we have a couple of crates which we created, the JSON patch and like the crate that I created for data-driven tests. So you have your test written as like data files that will generate like Rust tests out of it. And also I created and like this, I had this crazy experiment of building vtables at runtime, which I called Trader, but it's marked as dynamite. It's like you never should use it. It uses like a lot of undefined like behavior. Like it has a lot of undefined behavior in it, but it's pretty cool is that you can basically attach any trait to any data type, to any data instance. You can even attach different implementations of the same trade object to the same data instance. And I don't know, I find that was an exciting experiment. Anyway, and yeah, and that's all I have. And also we're hiring. So if you want to work on some of the exciting projects, you can join us. What do we have? Like, do we have Mike? Who's...
So with regards to your example number 2, looks to me like you don't really need to run code before main. You just need to know at compile time which things exist.
Exactly. Yeah. So if compiler would tell us, oh, by the way, I know that thread was implemented by those types, and give us that information in some way, that would solve that problem. Yeah.
Check out the link me crate.
Which crate?
Link me.
Link me.
Yeah. And there's currently actually a discussion on the internals forum about exactly this functionality.
Yeah.
Why was the context functionality in failure not sufficient for attaching auxiliary data to error types?
Why context information was not sufficient? I think it comes to all these like requirements. So if you drop some of them, you can use context. I think the problem was that if you use different context types, so like in the end, what you're getting is, okay, you have this trade object fail, and you have functionality to scan for this chain, and every element would be this trade object fail. Like now, what you're gonna do from that point? So the only thing you can do, like two things you can do. You can ask that fail trade object, give me your string representation, like text message, and that's it. And the other functionality is that, can you downcast to that specific type? So the question is like, what specific type would you use? Like how do you extract that? I guess it would be possible to do it in a way that we would use a specific context, and a string representation would be some sort of JSON, and we can convert the whole error chain in a string and then parse JSON and extract information. Like that would be possible, I think. But like you cannot ask this context for any specific functionality, because you cannot call like our own custom function on it to get this extra information. So that's kind of the way I see it.
I might just be misremembering. I was under the impression that context could be any data type. Is it required to be string?
Oh, so there's like another requirement of a universal data type comes in. So if you have just the context and you're wrapping in a context and you're wrapping in a context again, yeah, you can have a function that'll destructure this whole chain back into like specific data types and be like fully statically typed. But once you introduce this universal error type, like this failure or error, like the whole error thing, the whole type information is hidden. Like you get this error, is like there's nothing you can do except for this like dynamic functionality, like downcasting it.
Okay, thanks.
So you mentioned that Rust kind of lives in two different worlds with borrowed and
Yeah.
owned data.
Yeah.
Have you used the cow type from the standard library much to try to rectify that?
We use in some places, but I think the cow data type, it's kind of unifies these two worlds in like in a weird manner. Is that it either has lifetime and you're borrowing, but then otherwise you just well, whatever, I'm just making the whole copy of thing and moving around. So, and in case of like transaction, we can't really clone a transaction and have our own version of that. It still has this lifetime, so that's problematic.
Yeah, I have a lot of crates that use like static cow, and then it's like you can like at least have static allocated memory or owned memory, and that's pretty useful.
Yeah, I think static cow, like, I would say, like, honestly, I think the functionality of static cow should be provided by the string itself. And I think there was some RFCs about that. It should be possible to create string object without any allocations out of memory that you already have, like, statically allocated, like, for string static allocated. If you have that, you wouldn't even need cow. Like it's a very, very silly example. Like the string itself internally could have like a bit in its pointer address, like a lower bit saying, well, if I'm like static string or if I'm own string, and behave differently on drop. Like if it's own string, I would drop it. Otherwise, that's the str, and like I'm not going to drop it. I think. I mean, there are like details. Like if you're even allowed to use like extra bits inside pointers, you probably like should like it's probably very specific to a platform or something. But all right.
Thank you. We still have this space for quite a while, so feel free to hang out, eat more, and talk. Thanks all for being here.